Hello and good day. My name is Goven and Barrera. I am part of group number 5 and I will be the one who will be doing the live simulation of our project, which is a voltage regulated power supply from 220 volts RMS alternating current into a voltage output of a linear voltage which varies from 26 volts, 20 volts, 10 volts, 4 volts, and finally 0 volts. So let me first build our uh, our group's uh, power supply circuit. And so we have already calculated the necessary voltages. So starting with the input, or this one is the primary peak voltage. So we have to convert the RMS voltage into a peak voltage value. And so in order to do that, we would have to multiply the RMS voltage to square root of 2. And so it would yield to 311.127 volts. So by inputting that in LT Spice, uh, the amplitude would be 311.127 at a frequency of 60 Hz. So for the power supply, we will be making use of a step-down transformer in order to reduce the 220 volts RMS voltage into something that is close to the value that we would be looking to be that we would want to be the output. So unfortunately, there are no transformer models in LT Spice, and so we have to make one on our own using the available uh, inductors, inductor models in LT Spice. So in order to build one, we would have to place these inductors side by side as follows. We would have to ground them. Oops. And set the series resistance to be something that is negligible. And so step-down transformers, they reduce the voltage from the primary and into the secondary. And so the group has already computed it ahead of time. And so the turns ratio of the transformer that we will be making use of is a 3 to 22 step-down transformer. So this value right here is the turns ratio. So in order to use the inductors, we would have to first convert the turns ratio into the specified uh, inductances of the step-down transformer. And so by squaring the turns ratio, we would it would result to this value 9 over 484, and that is what we have to use for our step-down transformer. And now it is time for us to join these uh, inductors together and tell LT Spice that we mean to use it as a transformer. So by typing this following Spice directive, oops, need to rotate this. Yeah. So by doing so, we can now run the program. Oh, sorry, the circuit. We can simulate the circuit. I will be using a stop time of 1 second. This is a transient simulation. So we just have to set the load resistance. In this case, I would use 1000 ohms just to show you the oops. Just to show you the waveforms. So here in the primary winding, we would be having a peak voltage of it is nearly the same. Do note that uh, the voltages from here on are not in the ideal setting, so there will be some discrepancies, although they will be somewhat negligible, and it would be close to the actual value or the theoretical value, and so we can just approximate them to be the same. And so now that I have shown you the the input waveform for the transformer, we should also show this one. So this one right here is um, this is the secondary voltage after the input voltage has passed through the transformer. And now we can read the voltage as 42.24 volts, which is really close to the 30 volt RMS value, which we transformed it down, so, or rather step down. So now it is time to construct the rectifying circuit in order to actually make use of the 220 volt RMS alternating current. So the way to do that is to use 4 diodes. Um, by the way, the type of rectifying circuit that the group built was a bridge type full wave rectifier, because it is much more efficient than the center tapped one. And so by connecting the circuit as shown, we will be able to build the uh, the power supply circuit that the group uh, has created before. So there we would be making use of the diode 1N914, as we know this diode as a silicon diode, which means that it would have a voltage drop of 0.7 volts. So in order for us to see uh, what the output will look like once it is rectified, we will be simulating it. Okay. So this is um, the rectified waveform of the secondary voltage input. And so here we have shown that in this calculation that the uh, the input, which is the one that I have shown you earlier, will be subtracted by a value of 1.4 volts. And the reason why that is 1.4 volts is because the current passes through two of these diodes at any instance of the alternating phases of the current. And so the value theoretically in the ideal setting would be 41.106, but this in the simulation that I have shown you here, it is sort of close to that value. And as I have said before, it is because there are some discrepancies because the simulation is not in the is not conducted in the ideal manner. So some sort of uh, factors that would simulate reality would come into play. So now that I would be uh, building, the next step is the filter capacitor segment in order to further smoothen this already rectified waveform. And so the group has chosen a 2200 microfarad capacitor. By the way, these resistors are just load resistors. Okay, so by simulating it again, here, by zooming into the waveform, oops, you can see that the difference between the cursor 2 and cursor number 1 is around 103 millivolts. So that is the value that we have computed because it is already somewhat smoothened to a point wherein the Zener diode does not have to smoothen it any further. So as you can see, there is some sort of large discrepancy, but this value is already negligible since we are already uh, in the millivolts scale. So yeah. So now it is time to build the actual voltage regulator that will be producing the output voltage of the ones that I have mentioned before, the 26 volts, 20 volts, 10 volts, and 4 volts voltage outputs. So in order to do that, we would have to use what is called a Zener diode, which could be found here. Zener diodes regulate the uh, further linearizes this already um, somewhat smoothened waveform. So for the first output, this one that I will be making is the 26 volts output. So the diode that we would be using is this one from ROM, BZX8, something like that. It is included in our IEEE documentation, so it's just the same as like here. Oops. It is similar here to what we've built. So this Zener diode is rated at a breakdown voltage of 27 volts, meaning to say that it will regulate voltage at 27 volts. However, the voltage level that we want is 26 volts. So what the group decided to do is to attach a voltage divider circuit to the side of this Zener diode. So the calculations for the Zener diode voltage drop, for the voltage divider are as follows. So these are already pre-computed and are included in our documentation. The value for the first resistor is 38.462. Okay. Oops. So now that the output here was shown, um, it is now time to simulate it. And so the output here as shown is, but this is 27. Sorry. So at this junction here, at this corner, the output, or sorry, the voltage at this specified point is 27 volts. And as I have said earlier, that is not something, that is not the target output that we want. And so by making that voltage drop using these two series resistors to 26 volts, yeah, so that's what the group did in order to reduce the excess 1 volt. And so from here, you can see here in the vertical that the voltage, the values are pretty consistent. In fact, it is actually consistent because as you can see here, I am dragging this crosshair across this entire 1 second stop time, and so far I could tell that the voltage only varies by about a magnitude of a microvolt, and so it is really stable. So now it is time to construct um, the other voltage outputs, and so to do that we would have to extend our circuit, again 100. These resistors are, by the way, these resistors are there to limit the current passing through this Zener diode, because the Zener diodes actually have a maximum power rating, and we do not want the current to be too large because it would actually damage the Zener diode. And in this simulation, as you can see, it works, meaning to say that we have done the right calculations. And so again, by attaching another one of the Zener diodes, we would be able to produce another how did right we would be able to produce another voltage output. This time it would be the 20 volts. So again, the manufacturer is ROM and the diode type is a Zener type, so this one is rated at 20 volts. So by running it again and simulating it, we would get a 20 volt linear output. So again, as I drag this crosshair across the graph, the waveform, it looks really like a line at this point. And again, the voltage varies only by microvolts, so that variation is already negligible, and it is considerably stable. And furthermore, attaching uh, the other voltage outputs, we would again use the Zener diodes in order for us to further uh, decrease the voltage. So this time the Zener diode that we will be using is one of the 10 volt. Is it 10 volt? 620 and 10. So 10 volts. Right. So this time the manufacturer is on semi. Oops. So again, by running it, you can see that the um, the output is pretty much stable. However, it is not really that stable, unlike the other two. So what the group did was still use the Zener diode. However, make use of the another one of the voltage divider circuits. So now I will just be copying the diode that we made use of. I think it was BZX84B. Here. And so, as you have seen there, the voltage that this diode is rated for is 12 volts. So we have to reduce that again by using or making use of the voltage divider circuit. The out. This is 20 V out. So again, we have already computed this. The resistor for this one should be 200. Now by running it, oops, here we can see that it is much more closer to 12 volts, wherein the previous diode that we used outputted a voltage output signal of 12.8 volts, so that is an 8 volt difference. So here again, it is only varying by as much as a few microvolts. Sorry. So now it is time to do the 4 volts 4 volts output. I will just be copying this. Copy. Although we would have to replace the what do you call this, the Zener diode. And so unfortunately again, uh, there are limited models in LT Spice as shown here. It is cut off to 4.7, and there is actually no model that we've found that we could also import that could provide us a stable voltage regulation of about 4 volts. So again, in order to uh, for us to reach a voltage output of a flat 4 volts, we would have to again build a voltage regulator. Sorry, voltage divider. Output. So from what we have computed, it is actually 225 ohms in order for us to get a result of 4 volts. So again, by dragging the crosshair, it is really close. We can approximate it as 4 volts at this point already. The again the voltage only varies by only about a microvolt. So it is already stable. So finally, for the 0 volts, and this is another thing that is absent in LT spice, which are the switches, unlike in multisim. However, multisim needs a subscription. So by running this now, you can see that even though I click on it, there is nothing that shows. So it just means that the circuit is a 0 volt. So as shown here on the graph. So that is all that is to it, to our to the power supply circuit that Group 5 has built. Again, my name is Goven M. Barrera, and my other group mates are Mr. Nico Manalo and Miss Jasmine MAQUIRANG. Thank you for your attention.